Hi, this is Steve Sincere here to tell you a little bit about engineering methods in designing screen enclosures. There are several things that go into the design of a screen enclosure. First, the design wind speed requirement must be determined. Once this is established, the associated design pressures can be looked up in the Florida Building Code. Then the frame can be designed, and connections must be designed to hold the frame together. The wind speed requirements come from the Florida Building Code. The required design speed can be anywhere from 105 to 170 miles per hour. It depends on where the enclosure is going to be built on the map of Florida. The exposure factor also applies, which is considering the roughness of the surrounding terrain. For instance, if you're on a golf course or lake, you have a much greater exposure to the wind than if you were in a densely populated community. Design pressures are defined by the Florida Building Code and are based on wind speed and exposure, as previously discussed. In addition, factors for the mean height of the enclosure and the screen type may apply. These are used to determine the forces that the wind puts into every screen panel in the enclosure. These also vary depending on the orientation of the panel relative to the direction of the wind. Pressures are different for wall and roof panels. In addition, pressures are different for wall panels that face the wind versus walls that face away from the wind. And pressures on the roof are to be considered in both the up and down directions. In total, there are 8 different combinations of wind pressure that should be considered on an enclosure. There are 3 different methods to designing a screen enclosure. There's a simplified analysis method, there's a design manual or cookbook method, and there's the full frame 3-dimensional simulation method. The simplified analysis method is used by most engineers in the industry. This method is used to design the bulk of the screen enclosure frame, and it considers only the roof beam and the wall column. These pieces are assumed to be hinged together so that they can freely rotate about each other. However, no interaction with any other piece of the frame is considered. Engineers will typically use spreadsheets to develop span tables for sizing these beams and columns. These tables use all the same mathematical formulas. A separate table is developed for each combination of wind speed and exposure. Thus, the engineer is often just looking up values in predefined tables to size frame pieces when he designs a screen enclosure. The design manual or cookbook method uses the same simplified analysis to develop a series of span tables for sizing the frame. These tables are assembled into a design manual that contractors then use to determine what size pieces to use throughout the frame. This allows someone with no engineering education to engineer a structural frame. This is a typical span table from a design manual. These design manuals use a complex system of tables based on several factors: exposure, wind speed, roof style, wall height, and screen type. Once all these are known, the appropriate table can be found. And then the span and spacing must be correctly determined to find out what size material is to be used in the frame. Design manuals have hundreds of these tables. It's easy to make a mistake. It's also easy to skew the material selection to the next smaller size. And since building inspectors rarely verify the heights, spans, and spacing, this can go unchecked. The full frame 3D simulation method models the entire frame in a 3-dimensional virtual world. All pieces of the frame are designated to interact with each other, and wind pressures are applied to the entire frame for all 8 combinations of wind directions. The analysis accurately predicts the behavior of the entire frame in hurricane-force winds, and then computer programming evaluates every foot of the entire frame to search for weak spots. This is the most accurate, the most comprehensive analysis available in the industry today. These are the results of a full frame 3-dimensional analysis on a typical enclosure. The items that you see turning red would actually fail under the simulated conditions. As you can see, there are some conditions which are not very detrimental to the enclosure, while others are nearly catastrophic. This also gives you a good idea of just how many conditions need to be analyzed to fully ensure that your enclosure will hold up to hurricane winds. Connections are the nuts, bolts, screws, and other miscellaneous hardware that hold the individual pieces of the frame together and anchor it to the house and patio. In many cases, these connections are subjected to thousands of pounds of force, and the connections must be strong enough to hold these loads or they'll fail, which can lead to partial or total collapse of the screen enclosure. Connections are typically designed for ease of assembly and installation. Design manuals also prescribe connection designs, often with several options for the same connection, but rarely give any ratings for strength. Designing to maximum possible loads is the surest path to adequate connection strength. This means designing to the greatest forces that the frame will put into these connections. These maximum forces can be determined by knowing the size of the frame pieces being connected together. Thus, connections can be designed that will not fail. So what are the best engineering methods when designing a screen enclosure? For frame design, nothing can compete with the accuracy of the full frame 3-dimensional simulation. For connection design, designing to maximum forces assures against connection failures. For screen enclosure designs that can actually hold up to hurricane winds, please give me a call, Steve Sincere, Professional Engineer. And thanks for watching.